Hello folks, we're going to be talking today about inverse kinematics, and this is going to be covered in Robotic Systems Chapter 6, in particular 6.1 and 6.5 through 8. So the problem of inverse kinematics is that we have a desired position of some point on the robot that we'd like to reach some target location. And now we'd like to figure out what joint angles will be used to reach it. So from this particular point marked in black here and a target point marked in red, I'd like to find a solution that looks something like this, where I move my joints to actually reach the target. So there's lots of applications of inverse kinematics. The first one is trying to reach different targets, and we're going to be using a lot of this in pick and place. But also we use inverse kinematics to achieve continuous Cartesian motion. So if we wanted to, for example, move our hand along some sort of workspace trajectory to draw out some curve, we'd use inverse kinematics to achieve that motion. So the basic problem is going to look at just Cartesian positions. We have a point P on link N, and we want it to reach some desired target point in the world coordinates, PD. We know the local coordinates of this point, so those are going to stay constant, but the world coordinates are going to depend on the configuration Q, which is what we want to solve for. So the goal is for us to find a value of Q such that this equation here is satisfied. So the world coordinates of P match PD, the desired target. In general, IK can try to solve for a wide diversity of different types of constraints, not just positions. So we could include, for example, orientations. We could also include various axes. And in general, we're going to be solving some sort of constraint equation on the configuration Q. So some value x as a function of Q is equal to desired values x sub d. Note that this is a vector-valued function of a vector quantity Q. So x here denotes what's known as the task space coordinates. This can include a wide variety of different things, positions, orientations. It can also include constraints on multiple links of the robot. So for example, if you had a two-armed robot, you could tell the robot to grab an object with both hands. So for example, for a hinge constraint, I would constrain the position of some point on the end effector to some point in the world, and I would constrain some axis of my gripper to some axis in the world. So here we would have 6 different constraint equations. So there are 2 general approaches to solve inverse kinematics problems. There's analytical approaches, which actually try to write out the terms of the equation in terms of the values of Q, and then invert this equation to find out what the values of Q should be that meet the inequalities in this constraint. Sometimes there's simple solutions for certain types of kinematic structures and tasks, and these can be very fast. Alternatively, we can look at numerical approaches, which iteratively move a guessed configuration towards a solution point. Now, the first class of approaches is going to be the subject of other Intro to Robotics classes, and so we won't talk about that too much today. But instead we'll be talking about numerical approaches, which are very general purpose. They can incorporate things like constraints, but they do have a drawback in that they fall into what's known as local minima. So let's start out by casting this problem as a root finding problem. Essentially what we're doing is forming a constraint error function, which looks at the difference between where our task space coordinates currently are and where we want them to be. We want to then solve for this function f of q so that this error function is 0. So the general idea of numerical inverse kinematics is that we take this root finding problem and some seed guess, q0, and we're going to take steps towards a solution point such that the error of this constraint value, the norm of this constraint error function, shrinks towards 0. And then we'll stop when this process gets to a small enough error or when we can't make any more progress towards shrinking that error. So for example, from that starting configuration, we're going to move towards this point and eventually, hopefully, reach the point. We'll be briefly covering 3 numerical methods. There's many other methods, but we'll talk about 3 different representatives of different classes of method: cyclic coordinate descent, Newton-Raphson root finding, and also various minimization methods, including gradient descent. So cyclic coordinate descent is perhaps one of the first and earliest ways of looking at inverse kinematics. we think about having the robot at its current location, current pose, and what we'll try to do is incrementally change just a single joint at a given time to reach the target. So if my finger is supposed to reach this target point over here, I can, for example, move my shoulder joint to get fairly close. I can then move my elbow joint to get closer, move my shoulder again, and hopefully eventually converge and settle down to low error. So the idea is that we loop through the joints, which is the cyclic part of cyclic coordinate descent, and the point of the coordinate term in cyclic coordinate descent is that we're working with a single coordinate at once. So we do need to have some sort of way of calculating the minimum angle to reach this point, reach the minimum of this error function, and if we do so, we can end up seeing that this can converge reasonably quickly for certain cases. However, it has relatively slow convergence rates for some target locations that are close to extrema, which we'll soon see are known as singularities. Newton-Raphson method has somewhat better convergence rates than CCD, and it's basically a multidimensional analog of Newton's method. You should have had in your calculus class some definition of Newton's method that looks something like this. We find a step, we take a guess for a given position x. We want to find a position x that makes f of x equal to 0. And so we're going to find the step delta x by solving a first order Taylor expansion of the function f. And then we'll solve this to give delta x is equal to negative f of x divided by f prime of x, its derivative. So Newton's method looks something like this. We're given an initial guess x0. We evaluate f of x and we evaluate its tangent, and then we construct this approximating line to the f of x point at x0. We then find where this tangent line crosses the x-axis, and then that takes us to our new point x1. Then starting from x1, we'll do the same thing. We'll construct another approximating line, and then we'll find the intersection point with this tangent line and the x-axis, and then we'll repeat. And we can see that with a few iterations, we're getting very, very close to the point at which this function crosses the x-axis. So with the Newton-Raphson method, it's basically doing the same type of thing, but in n-dimensional space. We're solving this first order Taylor expansion here, where f of qi plus this thing over here, it looks fairly scary right now, times delta qi is equal to 0. Now this term here is going to be what's known as the Jacobian matrix, which is a matrix of partial derivatives of f with respect to q. If your multivariable calculus is a bit rusty, the Jacobian of a function f, where it takes in input q and outputs a vector x, is the matrix of partial derivatives, given by this expression here. If the output has m dimensions and the input has n dimensions, this is an m by n matrix, and the entry in the ith row and the jth column is going to be the derivative of the ith entry of f with respect to the jth value of q. This is typically written j of q, and it's also dependent on q. So just as an example, if we take, for example, the task space of the position of a single joint robot. So basically there's just a rotation about the axis, the arm length has length L, and this point is now xy. As a function of q, which is just the single joint angle, this is going to give us L cosine q, L sine q. If I were to then compute the Jacobian of this transform, I have two outputs, so it's going to have two rows, and I have one input, so it's going to have one column. And so if I calculate this Jacobian here, it's going to be negative L sine q in the first element and then L cosine q in the second element. Note that this vector here, if we were to interpret this column of j as a vector, it's going to be pointing with the same magnitude as L, as xy, and it's going to be pointing in an orthogonal direction. So this gives rise to a very important interpretation of the Jacobian matrix, which is that if q were to change at unit speed, j of q is going to be the velocity of my target point. More generally, if I have a joint velocity, then multiplying the Jacobian matrix times the velocity vector is going to give me my task space velocity x dot. So for example, if j of q is pointing in this direction, and I were to interpret that as a vector coming out of my task space point, then if I were to rotate less quickly in the positive direction, then that's just going to scale the instantaneous velocity of that point. Also, if I were to be rotating this joint angle in the reverse direction, my velocity is going to go in the opposite direction. So getting back to how this relates to Taylor expansion is that we've seen the one-dimensional Taylor expansion from calculus. Now, the first order approximation is given by the function evaluated at x plus its tangent evaluated at x times the delta x plus some small term. Now, for an n-dimensional function, the first order Taylor expansion is very similar. It's equal to f of x plus the Jacobian of x times delta x plus some second order term. Note that these approximations assume that the first and second derivatives exist and are bounded. So the Jacobian matrix can have multiple different types for a robot. So if you're just looking at positions, the position Jacobian gives us the derivative of some point attached to the link. So this is going to have 2 rows in 2 dimensions and n columns, where n is the number of joints in your robot, and it's going to have 3 rows in 3D. The orientation Jacobian is a little bit more complex. It's going to represent what's known as the angular velocity of a rotation matrix for one of the links of the robot. In 2 dimensions, the derivative of a rotation matrix has an interesting form. If I have theta as a function of some parameter u, doesn't matter what u is, the derivative of the rotation matrix with respect to u is going to be the derivative of theta with respect to u times this off-diagonal skew-symmetric matrix here that has 1 and -1 and its off-diagonals times the rotation matrix itself. The orientation Jacobian is going to give me the derivative of theta with respect to q. It's going to be a 1 by n dimensional matrix. In 3 dimensions, we're not going to prove this, but the derivative of a rotation matrix with respect to u, some parameter, is going to be the cross product matrix of some vector omega u, which is known as the angular velocity vector, times r. So the Jacobian is going to give me in its columns these angular velocity vectors induced by derivatives with respect to each of the joint angles. So it's going to be a 3 by n matrix. Now, if I want to then stack these together, I'll get what's known as the total Jacobian, which is going to have either 3 rows in 2D or 6 rows in 3D. Now that we have these types of Jacobians, we can start to move forward and try to solve Newton-Raphson. So here I have delta f over delta q, which is the Jacobian matrix. What I want to then find is some value delta q that solves this equation. Now, I may not have the same number of input variables as output variables, so m may not be equal to n. In other words, the Jacobian may not be square, but I can still seek a solution to this equation using what's known as the pseudo-inverse. So the pseudo-inverse is defined for any matrix. It's usually denoted by a superscript plus sign, and the pseudo-inverse has lots of different interesting functionality, including almost solving this equation. If it does have a solution, it will actually produce a delta q that solves the equation to 0 error. If this equation does not have a solution, then it will solve it to minimum error. So these pseudo-inverses have a lot of really nice properties. I'm not going to get into the details here, but you can pause the video and take a look at all of these nice properties. So getting back into the Newton-Raphson method, if we were to examine what happens when we run this, oftentimes it converges very well. But like normal Newton's method, it can suffer from what's known as divergence. So in this case here, for just plain Newton's method, we start out with this point x1. We then apply our standard transformation, and if you were to repeat this over and over again, you'd see that we're actually getting farther and farther away from a root to the point where, in this case, it would actually diverge to infinity. So this type of problem happens actually more often than you might think. And so we usually need to combine this standard pseudo-inverse approach with what's known as a line search to prevent divergence of the algorithm. The ultimate algorithm is a bit complicated, but in any case, we try to figure out a way to decrease the amount that we move in this delta q direction such that we sufficiently decrease our error function value. So what this looks like is that we have some sort of mental potential landscape where this is the error function, and we have some point in a direction that we found using this pseudo-inverse technique. We can then imagine looking at a line of possible step sizes along this delta q direction. And if we're to look at the error function value on the y-axis, and the x-axis is the amount that I'm moving along that value along that axis, I can find some optimal step size that would get me to the minimum error point along that step direction. So this is the general idea of line search. Next, let's take a look at some minimization methods. Each of these methods defines the scalar error function as some function of the constraint error function, like, for example, the norm of the constraint error squared, and they try to directly minimize this function. A very common approach is known as gradient descent. Here we take steps in the negative gradient direction of the function g. The gradient direction is this vector of partial derivatives, and it gives the direction of steepest ascent of g. It's related to the Jacobian matrix through this equation here. The gradient of g is equal to 2 times the Jacobian transpose times f. Now this works, but it can be actually rather slow to converge. It has what's known as order 1 convergence. A better approach is known as Newton's method, which is another technique that tries to actually use what's known as second order methods to actually do root finding on the gradient function itself. It has order 2 convergence, but one of the downsides of this is that it requires calculating what's known as the Hessian matrix of each entry of our function f. The Hessian is the matrix of second derivatives, and it's much more complex to calculate than the Jacobian. Finally, we'll briefly mention quasi-Newton methods that are trying to come up with an approximate Hessian using finite differencing. If you've heard of the secant method for one-dimensional minimization, this is the multi-dimensional analog of the secant method. There are many nice things about numerical IK methods. For one, it's very easy to define new task types. We can constrain multiple points on the robot. We can constrain position and or orientation or axes. And so it's very versatile. But one of the problems is that it's somewhat hard to diagnose failures. We can't tell whether or not we have a target that's out of reach, or maybe we've just had a bad initialization and we've settled into a local optimum. So the local optimum problem, or local minimum problem, is that not all points that you start from, that seed configuration, may not take us to the ultimate global minimum. It may not actually solve the constraint equation that we've defined to 0 error. And so if we have multiple local minima, there's actually surprisingly many minima when solving IK problems. We'll either need to have a lucky or good initialization, or we could also just use a technique called random restarts. The idea is fairly simple. We just pick an initial configuration at random. We try to solve IK using our favorite numerical technique, starting from the seed. If you succeed, you're done. Otherwise, you just repeat from step 1. Now you do this for up to n steps, and if you have a large number of n, you have a higher chance of success. The drawback of this approach is that if the problem is infeasible, so if I've defined a target that's too far away, then this will never find a solution just because one doesn't exist. And so I end up wasting more time with higher values of n. Okay, so we can talk about other types of constraints as well in IK solvers. For example, there could be hard constraints like joint limits. We also may want to avoid collisions during IK solving. We also may want to incorporate various soft preferences, like, for example, being close to the current configuration, such as minimizing the amount of movement that you undertake to reach a target. You may want to stay away from obstacles or otherwise look nice or human-like. These are oftentimes easiest to incorporate using minimization techniques. However, we do need to discuss constrained optimization techniques, which are somewhat beyond the scope of this course, but there are some readings that we have available for you to check out if you're interested in how to solve constrained optimization problems. As a recap, inverse kinematics tries to go from task space to a configuration. So we have a task space that's defined, we have a target task, and we want to then move the local position or orientation or axes of these links to that desired task's coordinates. Numerical IK solves either a root finding problem or a minimization problem, and it does so by iterating from some initial guess. We talked about CCD, Newton-Raphson methods, and some minimization methods. We also introduced the concept of the Jacobian matrix. This is very useful not just for solving IK problems, but other applications as well, such as finding relationships between joint velocities and workspace velocities, relating accuracies from joint positioning to workspace positioning, as well as converting from torques and forces from Cartesian forces to joint torques. We also mentioned the problem of local minima, and one way to mitigate this is with the approach of random restarts. That's it for now. I'll see you next time.